Hello everyone. I'm Wei Lin, an associate professor in the Department of Biomedical Engineering at National Cheng Kung University. Today, I'm pleased to present our research on an innovative rehabilitation system for stroke patients. We call it the Mixed Reality Mirror Therapy System. This system integrates the principles of mirror therapy with the immersive capabilities of mixed reality. We've also incorporated physical haptic feedback and EEG evaluation to enhance the therapeutic effect and monitor brain activity. In this presentation, I'll discuss the background of this technology, the system design, our research findings, and the potential of this system to improve stroke rehabilitation outcomes. Let's now highlight the key aspects of our mixed reality mirror therapy system. This system uniquely combines the strengths of augmented reality and virtual reality, creating an immersive mixed reality environment for stroke rehabilitation. This is the first study to apply this innovative approach to mirror therapy. We developed two distinct modes of therapy. Mode 1 focuses on mirror therapy with task-oriented objects in the mixed reality environment, providing engaging and interactive exercises for patients. Mode 2 incorporates a physical shell and projection, potentially adding a tactile dimension to the therapy. Critically, our system includes real-time EEG evaluation, allowing us to monitor brain activity during the therapy sessions. Our findings demonstrate that this system effectively stimulates the bilateral motor cortex, which is crucial for promoting motor recovery. This combination of features makes our mixed reality mirror therapy system a promising advancement in stroke rehabilitation technology. To understand the context of our research, let's first review some background information and relevant literature. Stroke is a leading cause of disability, and hemiparesis, which is weakness on one side of the body, is one of its most common consequences. Individuals with hemiparesis experience impaired movement and sensation, significantly impacting their daily lives. Mirror therapy has been a valuable tool in stroke rehabilitation. It utilizes a mirror to create a visual illusion of movement in the affected limb, which can activate the mirror neuron system and promote motor recovery. In recent years, researchers have explored the use of virtual reality and augmented reality in stroke rehabilitation. Virtual reality provides immersive, interactive environments for therapeutic exercises, while augmented reality can enhance real-world activities with virtual elements and feedback. Furthermore, EEG evaluation has been used to monitor brain activity during rehabilitation, providing valuable insights into the neural mechanisms underlying motor recovery. Our research builds upon this foundation, combining the strengths of mirror therapy, mixed reality, and EEG evaluation to develop a more effective and comprehensive approach for stroke rehabilitation. To understand the rationale behind our mixed reality mirror therapy system, let's examine the background and objective of our research. We started by analyzing the existing approaches to mirror therapy, particularly those utilizing virtual reality and augmented reality. Virtual reality mirror therapy, or MRMT, offers advantages like a wider field of view and the ability to interact with virtual objects. However, it can feel less engaging due to the completely virtual environment, and it often lacks tactile feedback. Augmented reality mirror therapy, or ARMT, provides a more grounded experience in the real environment with a 360 degrees view. However, it typically lacks the ability to interact with virtual objects and also suffers from a lack of tactile feedback. Our objective was to develop a mixed reality mirror therapy system, or MRMT, that combines the best of both worlds while addressing their limitations. As you can see, we've integrated key features like interaction with virtual objects, hand tracking, a 360 degrees view of the real environment, and importantly, haptic feedback. This approach aims to create a more immersive, engaging, and effective mirror therapy experience for stroke patients. Now, let's take a closer look at the system architecture of our mixed reality mirror therapy system. This diagram provides a visual overview of the key components and how they interact to create a seamless and effective rehabilitation experience. At the core of the system is the user, who interacts with the MR environment through a MetaQuest 3 headset. The headset's hand tracking capabilities allow for precise and natural interaction with virtual objects. The software system, developed using Unity and C#, creates the immersive rehabilitation scenes and manages the therapeutic exercises. The user interface, displayed within the MR environment, provides intuitive controls for selecting the hand, resetting the scene, and choosing between different therapy modes. To enhance the sense of immersion and provide realistic feedback, we've incorporated haptic feedback devices. These devices deliver tactile sensations to the user, making the virtual interactions feel more tangible. Finally, the system provides clear motion instructions to guide the user through the exercises, ensuring proper form and technique. This integrated system architecture allows for a personalized and engaging rehabilitation experience, combining the benefits of mixed reality, mirror therapy, and haptic feedback. Let's now delve into the software design methods we employ to create our mixed reality mirror therapy system. This diagram illustrates the key techniques and tools we utilize to develop the software components. To create the mirror projection, we use the Meta XR Interaction SDK to track hand movements and generate a mirrored hand in the virtual environment. The system accurately calculates the reflected position and rotation of the user's hand in any objects they grasp, maintaining a convincing illusion. We enabled pass-through mode using the Meta MR utility kit, allowing users to see their real surroundings while immersed in the mixed reality experience. We utilized 3D models from Unity Asset Store and created appropriate renders and colliders for them, ensuring realistic visuals and interactions within the virtual environment. To provide haptic feedback, we tracked both the user's hands and the controllers. The controller served as a reference point for delivering tactile sensations, enhancing the user's sense of immersion and interaction with the virtual objects. These software design methods allowed us to create a truly immersive and interactive mixed reality experience for mirror therapy. Now, let's see our mixed reality mirror therapy system in action. This video demonstrates the two modes of therapy we've developed. On the left, you can see Mode 1, which focuses on mirror therapy with task-oriented objects. In this example, the user is performing a grasp and place fruits exercise. As you can see, the user interacts with virtual fruits in the mixed reality environment, picking them up and placing them in designated locations. This type of interactive task encourages active participation and engagement in the therapy. On the right, we have Mode 2, which incorporates a physical shell and projection. In this example, the user is performing a grasp and transport apples exercise. Here, the user interacts with a physical object, likely a container or basket, that is augmented with virtual apples through projection. This combination of physical and virtual elements can provide a more comprehensive sensory experience, potentially enhancing motor learning and rehabilitation. As you can observe from this demonstration, our mixed reality mirror therapy system offers a versatile and engaging platform for stroke rehabilitation. To further investigate the neurophysiological effects of our mixed reality mirror therapy system, we conducted an EEG evaluation experiment. This slide outlines the experimental design and the EEG analysis methods. We recruited 5 healthy, right-handed participants who used both the VRMT and MRMT systems while their brain activity was monitored using a 15-channel EEG. There was a 1-week gap between the VRMT and MRMT sessions. During the sessions, participants performed right-hand rehabilitation exercises. Each system had trials consisting of a 60-second black screen period followed by 30 seconds of rehabilitation in Mode 1 and then Mode 2, repeated 3 times. It's important to note that no physical objects were used in VRMT Mode 2, virtual objects were used to mimic the movements of MRMT. The EEG data underwent preprocessing, including ICA and filtering. We then analyzed mu and beta ERD to assess the activation of the mirror neuron system, motor cortex, and wider brain networks. This EEG evaluation allowed us to gain a deeper understanding of how our mixed reality mirror therapy system influences brain activity and contributes to motor rehabilitation. Now, let's examine the results of our EEG evaluation. This slide presents the key findings from our analysis of brainwave activity during VRMT and MRMT. In the mu wave, which is associated with motor cortex activation, we observed a trend of suppression in both VRMT and MRMT. This indicates that both systems engage the brain regions involved in motor control. However, when we analyzed the beta wave, which is linked to interhemispheric communication, we found a more pronounced synchronization in MRMT. This suggests that MRMT might facilitate more efficient and coordinated brain activity between the two hemispheres, potentially leading to better rehabilitation outcomes. These EEG results provide further evidence that our mixed reality mirror therapy system effectively activates the motor cortex and promotes interhemispheric communication, which are crucial for motor recovery and rehabilitation. In conclusion, our research has successfully combined the advantages of augmented reality and virtual reality to create the first mixed reality mirror therapy system, or MRMT. This system offers several key features, including the ability to interact with virtual objects, accurate hand tracking, a 360 degrees pass-through environment, and haptic feedback. Our EEG evaluation demonstrated activation in motor-related brain areas and showed that MRMT elicits a higher bilateral synchronization response compared to VRMT, suggesting its potential for effective motor rehabilitation. Looking ahead, we have identified several areas for future work. We plan to enhance the game design within the MR environment to make the therapeutic exercises more engaging and motivating for patients. We also aim to explore the use of object detection to replace controller locating, potentially allowing for more natural and intuitive interactions. Furthermore, we will conduct studies with larger sample sizes and include stroke patients to further evaluate the effectiveness of MRMT. We will also explore additional EEG analysis techniques beyond ERD to gain a more comprehensive understanding of the neural mechanisms involved. We believe that MRMT holds great promise for improving stroke rehabilitation outcomes, and we are excited to continue this research to further develop and optimize this innovative technology. Here are my references.